This is a continuation of examples for RL and RC circuits. At this moment for this semester, we're only working on RL and RC circuits that are first order, which means you can reduce the circuit into a single resistor, single inductor with enough effort. So in the lecture on the step response of RL and RC circuits, we worked through the step response and then we came up with this general formula that's shown here at the top of the page, and this is the formula that we're going to be using as we work through these problems. So in this particular problem, we're given a circuit where a switch has been open for a very long time, which means that the circuit for all practical purposes can be considered DC. The current through the inductor is what we want to solve for. So our x of t in this example will be I of t. And so we have a condition initially where the switch is opened, and then at t equals 0 the situation changes and the switch closes. So we need to find three things. We need to find the initial inductor current, we need to find the final inductor current, and we need to find the time constant. So to find the initial current, let's look at t less than 0, just before the switch closes. Now just before the switch closes, the circuit looks like this. Here's my 25 kilo ohm. Now the inductor has been sitting for a very long time and we have DC conditions, so it looks like a short. Here's my 30 kilo ohms, and here's my 1 milliamp. And my current through the inductor, this switch was open, so it would have been in the circuit, but it's open, so it's not really relevant. So here's my current I. So this is what the circuit looks like for t less than 0. So what I want to find is I want to find I at 0 minus, which is what this circuit is sketched for. So it'd be pretty easy to do a source transformation there. So let's leave my 250. We'll leave my 25K. And for all practical purposes, I want the current through that 25K. I want this current. And then what I'm going to do is I'm going to do a source transformation on the 30K resistor and the 1 milliamp source. So when I do that, that'll be 30 volts. So now this is a single loop circuit. So if I do some combining, I'll have 220 volts. And these two resistors add in series to give me 55 kilo ohms. And if I, for the moment, ignore the inductor current that was labeled and just look at this circuit, I know, for example, that the current is going to flow in the clockwise direction because of the direction of the voltage source and the direction of the voltage drop across the 55 kilo ohm resistor. So I1 is 220 volts over 55 kilo ohms, which should reduce to 4 milliamps, or 4 times 10 to the minus 3 amps. Now notice that in my circuit where I solve for current, that's actually in the opposite direction from what I in the problem is defined. So I'll have an I of 0 minus, that'll equal minus 4 milliamps because it was defined in the opposite direction. So that's going to be my I naught. Now I need to figure out what is the final value of that current. So let's look at what happens after the switch closes. Now after the switch closes, let me use a different color just for illustrative purposes. So after the switch closes, this is a short. So for all intents and purposes, this voltage source is shorted out. All of its energy will go through the short So I can effectively, for t greater than 0, I can remove that from the circuit. It will only contribute to the current in the short here. It won't contribute anything to this inductor current. So what I then have is, for t greater than 0, the circuit's going to look like a 250 millihenry inductor in parallel with a 30 kilo ohm resistor and a 1 milliamp source. Because once this is shorted, this is a single common node and it's in common with this node. So these two elements are in parallel, and they're also in parallel with the 1 milliamp source. So this is an all parallel circuit. So so there's now a single inductor and a single resistor, and so we could find from the inductor's perspective, for the circuit where t is greater than 0, what the inductor sees if we kill the source, if we kill the current source, meaning we open circuit it, the inductor sees an R equivalent of 30 kilo ohms. So L over R, which is my time constant, excuse me, L over R, which is my time constant, will be 250 times 10 to the minus third divided by 30 times 10 to the third. And I believe if you simplify that, you get 8.33 times 10 to the minus 6 seconds. And once again, not an unreasonable time constant for a transient circuit. In fact, pretty accurate. All right, so that's my tau. So now I have x sub 0 and I have tau. What I need to do now is I need to find the final value of the inductor current. Now, the final value of the inductor current for t going to infinity, we are approaching a DC circuit again. And the reason we're approaching a DC circuit again is all of the transient effects have died away, and we're left with an inductor under DC conditions which looks like a short. So this inductor needs to be replaced with a short circuit. The 30 kilo ohm resistor is still there because we're still in the circuit for t greater than 0. My 1 milliamp source is still there. But the inductor, because we're letting time go to infinity so that all of our transient effects die away, the inductor now looks like a short, which means that the entire 1 milliamp of current will go through the inductor. So now let's come back. So that would be our I final. So now I of t, plugging into this formula, we take our final value, which is 1 milliamp. We add our initial value, which was minus 4 milliamps, minus our final value, 1 milliamp, e to the minus t over tau, which was 8.3 times 10 to the minus 6. So that's our answer, and you can simplify it, of course. It'll be 1 minus 5. Let me take that up here. Okay, somehow I have no pen response. So I will let you do that simplification. Super easy, just add the 4 and the 1 together. So this will be 1 minus 5 e to the minus t over 8.3 times 10 to the minus 6 million.